So we will start from the beam efficiency. Now, what is the beam efficiency? It is related to what? That we'll understand. Now, this beam efficiency, it is related to what? That is power transmitted or received. Whatever the power you are transmitting or receive. Receive in the case receiving antenna, transmitted in the case transmitting antenna. Most of the understanding, it is comparatively easy in case of the transmitting antenna, or it is also applicable for receiving antenna. So generally we consider in terms of the transmitting antenna, because for visualization it is easy. So for receiving also it can be considered. So power transmitted within a cone angle of theta. So this is what, whatever the power you are transmitting in a cone angle means this is a solid angle of particular cone angle theta, and power transmitted or received by the antenna. Okay. Now, what is this? This is what uh, power transmitted. Now we will see at a time only transmitted, so that discussion will not be confusing. So power transmitted within a cone angle. This is what one angle we have taken. Power transmitted in this angle and power transmitted to the entire angle. So it is again the dimensionless. Whatever the dimension is not there. So this theta one, it is the half angle for a cone within which the percentage of the total power is to be found. Okay. So beam efficiency is you are taking the whatever you stand for what? Radiation intensity. So most of the time we are taking a reference of radiation intensity, because here cone angle means solid angle we are taking. Wherever the solid angle reference we are taken, where u we are taking, that is radiation intensity. So this is what 0 to 2 pi, that is limit for phi, 0 to pi, that is limit for theta. And this is u theta pi sine theta d theta d phi, as we are considering a sphere. So this is what the radiation intensity, this way we can calculate for what? For the isotropic source. Always for the by the antenna means all the direction. So all the direction means we are considering an isotropic source. So for isotropic source, these limits are mentioned. Only the change in the limit, that is 0 to pi, and here only change is 0 to theta 1. So you are considering horizontal angle is same 0 to 2 pi. Vertical angle is only change, that is 0 to theta 1. So beam efficiency means when you will say your beam is efficient. Okay. These are the annotation what I have mentioned here. So I'll explain you in the term what we can use. So here beam efficiency, I'll take one example. Here maybe this is what the radiation pattern of any antenna. Okay. And in this, whatever this is only beam. Okay. So whatever this antenna is transmitting only in this beam. All the radiations, what it is transmitting is only in this beam. So can you tell me, if I am considering this angle, this particular angle, maybe the half power beam width, this angle I am considering, suppose this angle I am considering, we'll draw it, this angle, and this is what the solid angle, half power beam width. Now for this antenna is only transmitting in this angle only, no other way transmission. So can you tell me what will be the beam efficiency in terms of percentage? Use the above formula. This formula is there. Power transmitted within a cone angle theta 1. So this is what angle theta 1. And power transmitted by the antenna, total power transmitted. So this antenna, whatever the total power transmitted is only within this angle. So it has the 100% beam efficiency. Understood? Because this antenna is only transmitting the power, whatever the power it is transmitting, only in this beam. And we are taking this angle theta 1. Suppose this is angle theta 1, whatever this. So this is having 100% beam efficiency. But if I will take the another example, now this antenna has this back lobe. Suppose this is a back lobe. Okay. So this back lobe is there. Now this back lobe, this the front lobe, it contained 90% of the power. Okay. So this front lobe contained 90%. And this back lobe, uh, this is contained 90% of the change the color. So this is 90% of power. And this back lobe, it is contain 10% of the power. So what will be the efficiency of this antenna? Can anybody tell me?
90%.
None. It is simple because we are considering this angle, and in this angle 90% it is radiating, and uh, what it is radiating 90%, 10% in some other direction. I'll take some another thing. Okay, so again this 10% is there, but again my antenna has some side lobe. So this is what the side lobe 1, this is what the side lobe 2. Okay, two side lobes are there. Now what I'll have the this side lobe. Again this side lobe is having, upper side lobe is having 10%, this lower side lobe again 10%. Okay, and my back lobe is having 10%. So what is remain? 70% is remain in the this front lobe. So what will be the antenna beam efficiency?
70%.
It is simple, 70%, because in this angle, what 70% of transmission of the power is there, and the remaining 10% in the upper side lobe, 10% in the lower side lobe, 10% in the back lobe. So that's why this all other it is considering this way. So this is what very simple example to understand, that this example will give you the understanding of what understanding of beam efficiency. These are the very simple concept. These concepts are very simple, but if you will look in terms of the formula directly, then it will become complicated, because mathematics you can implement. So same example I have put up here. So this is what the beam efficiency. Is there any doubt? It is a very simple
No,
concept.
sir.
So it is very simple concept. Only here uh, you are considering for isotopic source and particular angle, that is 0 to theta 1. And remember here we are considering vertical angle. Horizontal angle is 0 to 2 pi. That is same. That is what pi. So two angle we are considering. What two angle? One is horizontal angle. Door example. This is your pi. When you will open a door, this angle is horizontal angle. So this is angle is pi. And when you will have the vertical angle, this is z axis and this is vertical angle. So this is what your theta. This is what your theta. So you remember this. So your angle notation will be clear. So this is what a beam efficiency. Simple example for the beam efficiency. Now this is what simple. Now we will go to the next. Now this is what the important parameter. Directivity, beam efficiency, now gain. Now the gain, it is similar to the directivity. It is somewhat, you can say, is relate to the directivity. We are going to understand the relation between gain and directivity also here. So gain, if you remember, directivity, if you remember, So directivity is related to the radiation intensity. Now gain. Now if you can correlate this with the gain of any amplifier, because you have the background. So gain is simply the output upon input is gain. Suppose you have an amplifier. Okay. So suppose you have an amplifier. The amplifier has certain input. So you are giving certain input and the amplifier is doing the amplification. Suppose the input is 1 volt sinusoidal and you are getting 2 volt. So gain is 2 by 1 is a double 2. This is what the simple logic you know. But in the antenna, this is not the simply way. This is not the way that it is considered in somewhat different way. How it is considered? So here, this is what it is closely related to the directional capacities, efficiency and directional capacity. Now, in the efficiency of antenna is a different parameter, and directivity or the directional capability is another parameter. Those two parameters are taken in consideration and combined and giving the gain. Okay, gain of antenna. So here, absolute gain of an antenna is a given direction is defined as the ratio of intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotopically. So it is what similar, you feel similar to the beam efficiency or similar to the directivity. So we will go in detail. So this radiation intensity correspond to the isotropic radiated power is equal to the power accepted, that is by the antenna divided by 4 pi. Why 4 pi? Solid angle of the sphere is 4 pi. Repeatedly I am saying this. This is what called the absolute gain. Again, the gain of antenna are of two types. One is the absolute gain, other is the relative gain. What is the relative gain? Generally, we calculate the relative gain. Absolute gain in some theory calculation they calculate, but generally the gain is calculated as a relative gain. What is relative gain? The ratio, relative gain is what is given here. It is what the ratio of the power gain in a given direction to the power gain of a reference antenna in its reference direction. The power input must be same for both the antennas. So here, what we are having here, we are considering the antennas in the two cases. Here, they are not mentioned in the definition, but one is the isotropic antenna and other one is the directive antenna. That is considered. What is absolute gain? Absolute gain in a given direction is defined as the ratio of intensity in a given direction to the radiation intensity that would obtain if the power accepted by the antenna were radiated isotopically. Now, if we will go in the definition, you feel it is somewhat complicated. Okay. So if you will go in a definition, you may not understand or may understand. But if you will go in an analogy of understanding, then very clearly you will understand. Now, what is this analogy? That I will try to explain you what is here. Okay. So here we can consider here gain, the formula for the gain. Here 4 pi is taken as constant. Radiation intensity, whatever the radiation intensity upon total input accepted power. So the radiation intensity in the particular direction. Okay. Now here radiation intensity U into theta 0. Just now we have seen the radiation intensity wattage. P in is what the total power accepted or the power, whatever the power P in. Okay. So the directivity and gain, they are related to each other. So radiated power replaced by the total input power P in, that is feed to the antenna. Now, what we are having difference between directivity. Directivity is also having the same formula, but only the thing is this P in, whatever the P in you are considering, the input power to the antenna. In the gain, you are considering the input power. In the directivity, you are considering the radiated power. Means what? Efficiency we are taking care. Okay. In the directivity, you are not considering the efficiency of antenna. In the gain, you are considering the efficiency of antenna. Means what? If you are giving 1 watt to the input to the antenna, and this antenna is transmitting 1 watt completely, radiating completely. So efficiency complete. Now I am talking about the efficiency of antenna. So antenna has the 100% efficiency. Okay. Now, in that case, if the antenna is having 100% efficiency, in that case, directivity and gain both are will be the same, because P radiated and P in. P radiated is what? Power radiated in a uh, 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 in a space, and P in, this is what the electrical power given to the antenna. So before, what is having, before giving, you are giving input to the power input to the antenna, and this antenna is radiating power. Now, if the radiated power and input power both are same, 1 watt you are giving input to the antenna, and this antenna is radiating 1 watt. So efficiency of antenna is 100%. It do not have any loss. But if you don't have the 100% efficiency, then different the directivity will be more and gain will be less. So here P radiated equals to P in into efficiency. If there is 100% efficiency, so P radiated and P in will be same, and your gain and directivity will be same. So simply P radiated and P gain, you can relate directivity, gain upon directivity, that is P radiated upon P in equals to efficiency of antenna. So if you know the gain of antenna, directivity of antenna, then you can calculate the efficiency of antenna. So most of the antenna, if you will say the most efficient antenna, maybe you can say 60 or 70% is the highest efficient antenna, maybe some of the antenna. We'll discuss later on. So here, this is what the analysis, this is the transmission line. This is power transmitted. Okay. So that is what the input power you are giving to the antenna. And this is what the power transmitted. So one simple thing you can remember here, the directivity and gain is related with the efficiency. So you can do relate with the efficiency. Direct gain upon directivity is equals to efficiency. If efficiency is 100%, both parameters will be same. Gain and directivity will be same. So why we require directivity already was there. So why we have introduced the gain? Because we require to know that how much is the efficiency. So this is what the overall complete parameter that is gain. So this is what the gain and directivity. Is there any confusion or question? Okay. Now we'll go for this consideration.
Sir, wait, sir, लिखना है.
Okay. So this is what the gain. This is important. That is power radiated and power input is related with the efficiency is efficiency of antenna. So the gain upon directivity is P radiated upon P in, that is E, that is antenna efficiency. This is what the thing here. This is the relation between gain and directivity. One of the example I will give. Now this example is for again the understanding purpose. So my focus here is your understanding. This formula you will remember. If you will understand the analogy, then you don't have to put much effort in remembering the formula. That will comes But these are the dependent formula. So you can just see that, so it will remember automatically. But if you will mug up it, then it will be horrible. Then nobody can save you. So focus on the understanding of the concept. Okay. Now this one. So radiation intensity that for a isotropic source. Now this is what the example given. This is the radiation intensity of a isotropic source, and the same radiation intensity actually that antenna is radiating in this given direction. So this is isotropic source and this is highly directive antenna. Maybe 30-degree or 40-degree will be the beam width of this antenna. So it is very highly directive. This is what the example for understanding. This antenna gain, whatever this antenna A, having the comparatively lesser gain, this antenna is having the high gain. Although they are transmitting the same power. Understand this statement very clearly. If this antenna is transmitting power 1 watt and this antenna is also transmitting a power of 1 watt, but the gain of this antenna is high as compared to this because it is radiating in a particular direction. So directivity of this antenna is high. So that's why gain of this antenna is high. I'll repeat again. Suppose this antenna A, it is an isotropic source. It is radiating 1 watt power. And this antenna, it is highly directive antenna. It is also radiating 1 watt power. But the directivity and gain of the antenna B is very, very high as compared to the isotropic source, although they are transmitting same power. Why? Because it is transmitting in a very short angle. So that's why gain and directivity of this antenna is multiple time of this isotropic source. This is what the difference of understanding between your simple understanding of amplifier gain and this antenna gain. Okay. So this is what the concept here I want to highlight. Now we will go for this parameter polarizing. So we will take this parameter. Now here for the polarization. So what is polarization? Now this is what the interesting parameter. What is polarization? Now this polarization, now if you will see the electrical thing of this polarization, then it will be I'll show this is what very interesting parameter. Oh, sorry. So this polarization, so the polarization of the antenna in a given direction is defined as the polarization of a wave transmitted radiated by the antenna. Polarization of a radiated wave is defined by that the property of electromagnetic wave described in the time varying direction and relative magnitude of the electric field vector. Now here, what is this important? Important thing is it is electric field vector. Magnitude, the relative magnitude and direction of electric field vector. So this is what the focus point. In the electromagnetic wave, what is there? In the electromagnetic wave, you will have electric field vector and magnetic field vector. So the electric field vector and magnetic field vector, now we are considering only one field vector, that is, this is electric field vector, magnetic field vector. Now magnetic or polarization understanding, we are considering the electric field. Now direction and magnitude of electric field vector we are considering here. Now here, this is what the polarization of this antenna. Okay. Now, what is this? That we will check it out. What is this polarization? Now, here some diagram will explain you. This is what I have shown you. This is electric field vector. This is magnetic field vector. Magnetic field vector mostly shown in a dotted form, and electric field vector is shown in the direct line. Now there are some types of the polarization. This is what called vertical polarization. So if your electric field vector moves vertically, so this is called vertical polarization. If it moves horizontally, this is called horizontal polarization. Both vertical and horizontal, both are called as linear polarization. This is what linear polarization. Linear polarization is bifurcated into two types, that is vertical and horizontal. What is that? That I'll show you. There is a fantastic simulation here, so you will understand completely. Now, there is the elliptical and the circular polarization. So what is that? That I'll explain you. So here,
सर वेट सर ड्रॉ कर दे
yes.
सर 1 मिनट सर डायग्राम ड्रॉ करना था
हाँ, मैं बता देता हूँ बाद में. You draw it afterwards, so you will understand it. I'll give you the understanding. That is the electric vector simply. So here, simply what notations you have? Linear polarization. The field vector is only component. Circular polarization, left-handed circular polarization or right-handed. Left-handed means it you are rotating by a left hand. This is left hand. That is what anticlockwise. A right-handed circular polarization. This right-handed anticlockwise. Both are given. Now here, both the polarization. Now this you can understand. Now this is what the linear polarization. What linear polarization? What I have given here. Now in the linear polarization, this is what you can just check. So the red one, whatever the red line is shown here, this red line is nothing but a electric field vector, and this is magnetic field vector. Now Poynting theorem is it is considering Poynting theorem properly. You just consider. Now this electric field vector red line is perpendicular to the magnetic field vector. This is electric field vector perpendicular to the magnetic field vector, and direction of propagation is this, is again perpendicular. So this is what all these three are perpendicular to each other. Now you just check what I am giving here. Now this is called the horizontal polarization. You see this is what the electric field vector. Now this electric field vector is projected here. Now when I remove this, when it will go, you can see the projection of this electric field vector here. It is rotating, is projected here. So this vector is moving horizontally. Here also it is moving horizontally. So this is called the linear polarization, but of which type? Horizontal. Okay. I hope this is what visible to you. Is it clearly visible? The movement. So here it is moving, and accordingly I'll just pause and show you what I mean to say. You just see the projection of this electric field vector here, same projection I have put here. So it is horizontally moving. It is what? the field vector, it is horizontally moving this way. So this is what we are taking. Remember it, it is the projection of what? Only what? It is the projection of only electric field vector in a horizontal. Now, what will be the vertical? What will be the vertical polarization? Now, if the projection is in this way, if the things are this way, so the vector, it will move vertically. So this is what the linear, this is again the same as previous linear polarization, but it is horizontal linear polarization. This is horizontal. So what is the difference here? The difference here is practical difference is what? So practical difference I'll see. Now suppose this is an antenna. Suppose this is an antenna. Okay. So it has a horizontal polarization, means this way it is rotating. So if you will transmit this way, so you need a horizontal polarized antenna. So the receiving antenna should be this way also, this way only. Okay. So both the antenna, suppose this is what one antenna horizontally polarized. This is horizontal polarized. It transmits horizontally. This is another antenna. Again, this is horizontally polarized. So this should be kept this way. ऐसे ही सामने सामने अगर रखेंगे, then and then it will be horizontally polarization match, and then they can be received. Okay, if they are horizontal polarized. If one is kept this way and one is kept this way, so that polarization mismatch will be there and not the optimum reception, maximum reception will not be there. Are you getting this? This is what, this is one antenna that is having horizontal polarization. This is another antenna having horizontal polarization. And both antennas are horizontally aligned, then they will receive the maximum radiation. One is transmitting, one is the receiving. Okay, so this way can be done. So this is what the polarization here. So this is the uh, vertical polarization. So one is the horizontal and another is the so this is what the thing here. This is the polarization. It works this way. Okay. Now, is there any doubt in vertical and horizontal polarization?
No, sir.
I don't think any, because it is simple and self-explanatory. Okay. Now we will go in a combine. Now, what is combine? Now here combine, you can see this. Now for this combine, you just see here what I did. This is your horizontal polarization. This is your vertical polarization. Same notation what was there previously. This is the simulation. The same way is taken. The horizontal and vertical, both the polarization A and this is vector B, both are connected. Only the thing is, you can see it has angle 0 and it has angle 90. Means what? I will show you. Means what? Now, oh, sorry. Now you can see. Now here, what is this angle? This is suppose angle 0. So it has the same magnitude and angle 90 degree. So here both are projected here. This is angle, this is horizontal polarization having angle 0. This is vertical having angle 90 degree. So phase shift between these two is 90. So this is what the vector addition. So this is the vector. When both will move, when this both vector they will move this way. This move horizontally, this move vertically. So it rotates. In what way? Left-handed circular polarization. That is clockwise. Left-handed circular polarization clockwise. This way it is move. And if how it happened? It combine this. It combine this and this both, and this is what rotating, because your electromagnetic wave never glow in a planar way, so it has some rotation. So that rotation can be uh, seen here. So this way you can see this vector is rotating. If this is a clockwise, so going from left side to right side. Left-handed means left side, starting point is from left side to right side. So this is what we can see clockwise. So from left side. So this is what left-handed circular polarization. Very simple to understand. But if you will go through only theory, this is extremely complicated concept. But this simulations explains you 10 page of explanation in a simple one loop. So this you can go and refer. So this is what the simple understand. Now, if I will change this angle as 90 degree to minus 90, then instead of left-handed circular polarization, it becomes right-handed circular polarization. Now, you just check this. This is a right-handed circular polarization. Now, you can see this. Now, this is angle 0. So it was this way. So it is 90 degree. So it is what, again 90 degree. Previously it was plus 90. Now it is minus 90. It is down. So this is what the vector sum of this, and it is rotating. Now rotation, you can see the rotation is anti-clockwise. So it is right-handed, starting from the right hand. Right-handed. So that is called anti-clockwise. Huh? But here notation for the polarization in circular polarization, again it has right-handed and left-handed. Right-handed means starting from right hand. Starting from right hand, anti-clockwise. Left-handed means starting from left hand, it is clockwise. Okay. So this way we can say the left-handed and right-handed circular polarization. This polarization is here, and this is circular. Now, the other polarization may also introduce. Now, here, whatever the magnitude of both the vector is same, maximum magnitude. Now, if the magnitude of both the vector will vary, so instead of circle, it become ellipse. So the researcher, designer, they struggle to get this polarization. Which one? Circular polarization. Because you can see the circular polarization is covering the entire element. But here you can see the linear polarization. This is the example of horizontal linear polarization. So linear polarization cover this much area. The vertical linear polarization only this much area, but it is covering the entire area. So if the same, if your circular polarization is there, so current induced in a antenna is new. Although if you will have the same gain antenna, but one is circular polarization, one is linear polarization. Circular polarization is always preferred because it induces more current. And although the gain and all the parameters are same, but always the circular polarization is preferred. So this is what we can say. This is what the circular polarization here. Any doubt here in the circular polarization?
Sir, we use the circular polarization in helical antennas.
Ah,
Okay.
correct. Helical antenna gives the circular polarization. Microstrip antennas also designed for the circular polarization. But by default, helical antenna gives the circular polarization. The other antennas also can be designed for the circular polarization. Your dipole antenna gives the linear polarization. It cannot be, you can say, designed for
That
this.
Yagi Ura antennas are linear
Yagi
polarization.
antenna is also circular, no, it is also the linear polarization.
Linear, right? Okay.
So
got it.
these are the mainly the example. The helical antenna gives circular polarization. Correct. Okay. So when we will study antenna in detail, that time we will give the example which antenna is giving which polarization. That also we can consider. Your dipole antenna
Okay.
gives linear polarization. Anything else? So this is what the understanding. If you will have clarity here, then you will have the very interesting thing in the if you will understand the basic parameter, then you will create an interest. So try to create. I am also doing try to create an interest for you in our learning process. Okay, so you also try to create your interest in the learning process. Okay, so we will go further. Now this polarization, some understanding and some other things are there. So polarization mismatch, generally, just now I have explained what is polarization mismatch. So polarization mismatch, it is what mismatch polarization of the receiving antenna, not the same as polarization of the incoming, that is the induced wave. So this polarization mismatch, although you will have a very high gain antenna, but if you will have a polarization mismatch, then it will not be useful. What is polarization mismatch? Suppose you are transmitting antenna. This is a one antenna. Okay, plain antenna. This antenna is having a horizontal color this way. So I kept horizontal. This antenna is also have a horizontal polarization, but I kept this way. Okay. So I kept this way. This is polarization mismatch. It is transmitting horizontally. Electric vector ऐसा rotate हो रहा है. इसका electric vector is rotating this way. It is also horizontal polarization. So if I kept one antenna this way, one antenna this way, both are linear, but both are horizontal. So this is what the polarization mismatch. And this polarization mismatch, although the gain, whatever the gain is there, it will not get the impact of that gain. So this is polarization mismatch. This is practical concept. When I gone to the industry and interact with the people, understand their problem and try to solve their problem, that time I come to know this is what the polarization mismatch. Then ratio of the power received by the antenna from the given plane wave of arbitrary polarization to the power that would be received by the same antenna from the plane wave of the same power flux density and the direction of propagation uh, whose set of polarization has been adjusted for a maximum received power. So this is what the polarization matching. What I'm saying, this both the horizontal transmitting and receiving antenna, so should be aligned this way. Okay, both the antenna should be aligned this way. So this is uh, what your polarization match and mismatch. Okay, so now this is what the effective length. Next parameter. What is effective length? Can you have any casing about what is effective length, or it also called the electrical length? Effective length of an antenna. So effective length of an antenna, what is the effective length of an antenna? So you just see This is what you can say the effective length. We just go through this. What is the effective length? The effective length is what? Effective length of an antenna can be given in this way. Effective length. What is the effective length? So for an for receiving antenna, it is defined as the ratio of induced voltage to the induced field. So effective length is the V by E in meters. That is ratio of induced voltage to the induced field. For you can say for transmitting antenna, this is what receiving antenna, and for transmitting antenna, effective length is the length of an um, a equivalent linear antenna that has the same current as that of the transmits of the actual antenna at all the points along its length, and that radiate the same field intensity E as actual antenna. So it is easy to understand for the receiving antenna. So for receiving antenna, it indicates that the voltage, that is what the receiving antenna is defined as the ratio of induced voltage to the incident field. What it mean? Meaning क्या है? Any antenna, again we will consider this as antenna. For this antenna, receiving antenna, the electromagnetic waves are there and it is induced. Here you can measure the physical length of this antenna. This is, but it is induced by the electric field, and by that electric field, how much voltage is induced in this. So how we can consider this? Okay, so here consider a vertical dipole of lambda by 2 length immersed in the inside in a field, whatever the field incident field is there, current distribution is uniform, the effective height would be L. Actual current distribution is nearly sinusoidal wave. The value that will be 0.642 by pi of the maximum. Hence, the effective length H equals to 0.64 into L. What it means? Final, this is what the important thing. This is what 0.64 into L. L is what? L is what the length of the antenna, physical length. Now, what is given here? The example of dipole. Dipole is, what is dipole? Is a line, is a wire, simple. So this is the dipole. So for a dipole antenna, effective length, suppose this is the 10 centimeter. This is what the actual physical length. Now, what is shown here? Formula, the height, the length, the actual height of H equals to 0.64 into L. So it is not 10 centimeter. Actually, physically it is 10 centimeter, but effectively it is less than 10 centimeter. How much it is? 0.64 into L. So it is 6.4 centimeter only. 0.64 into 10. So it is simply 6.4 centimeter. So whatever the effective length of the antenna is always less than the physical length. Okay. In this example, it is shown. What we are taken? We are taken the antenna. What? Lambda by 4, lambda by 2 antenna. It will change for the different antenna. If you will change the lambda, electrical dimension, if you change, it will change. So this is what we will see this detail. Don't worry about this example when we will go for the dipole antenna. So here, only the point I want to make here, that whatever the height, effective length of your antenna, effective height of, this is the dipole antenna. But for dipole antenna, this is what, although this is what, 10 centimeter, but it will not be. Physical length is 10 centimeter, but effective length is not 10 centimeter, it is 6.4 centimeter. Why? The whatever the waves induced to this, what is the impact of this is as good as this length is 6.4 centimeter. So what your effective length of an your antenna is always less than the physical length. So we are require these things in the design. So various antenna we have to design. So there in the design we have to calculate in terms of the effective length. Okay. So is this clear? This is very simple concept, nothing great. So whatever the impact it is giving, that is you can say the effective length. For this example, lambda by 2, it is giving impact of 0.64 L. That is 10 centimeter of physical length antenna give 6.4 centimeter only. Is it clear? Okay. Now we will go further. This is the effective length that we discussed. Now we will go further. Antenna bandwidth. Now, what is bandwidth? Is a simple concept. Bandwidth is very simple. What the understanding is there in the general bandwidth, the same understanding is here. There is no difference in the bandwidth. So it is what the higher frequency minus the range of frequency where the antenna uh, antenna operate. It is what the range of frequency. This is what the bandwidth of an antenna is defined as the range. It is the range of usable frequency within which the performance of antenna with reference to the same characteristics can be specified standard. Now here this is general definition. Usable frequency, whatever the frequency you are using, range of frequency for the specified character. So bandwidth in general for maybe your amplifier and all this, that is a single bandwidth. That is simple bandwidth means bandwidth. But here multiple bandwidths are there. Because if you are changing the parameter, the bandwidth will change. Now which parameter you are considering? Again the basic parameter. Now we'll see what are the bandwidths are there. The bandwidth can be range of frequency on either side of a center frequency, that you know, where the antenna characteristics like antenna characteristics like input impedance, whatever the antenna characteristics like input impedance, where correctly like input impedance, one, radiation pattern, beam width, polarization, side lobe level, gain are choose to those values with which have been obtained at the center frequency. Means what? Bandwidth, what we are considering the impedance bandwidth, input impedance bandwidth generally. When there is a impedance matching and giving the range of frequency, that is called input impedance bandwidth, impedance matching. But if you want a radiation pattern, particular radiation pattern, if you want a 40-degree radiation pattern, so that radiation pattern for what range of frequency? Beam width. Suppose you want beam width equals to 60 degree. So 60-degree beam width you got for which range of frequency? Then polarization. If you want a circular polarization, then for which range of frequency? Then side lobe level. In some of the example, side lobe separation is most important. Why it is important? Side lobe separation means you have a main lobe and the other are the side lobe. So side lobe separation is important. So their side lobe bandwidth, most of the example minus 14 dB. Minus 14 dB is one of the standard for the side lobe level. Then gain. If you want a constant gain, maybe 10 dB gain of antenna. So that 10 dB gain you are getting for which range of frequency? So we are considering here 1, 2, 3, 4, 5, 6 parameters. But they are not, we are not considering it in collectively combined. They are separate. Impedance bandwidth is one, radiation bandwidth is another, beamwidth bandwidth is third, polarization bandwidth is fourth, side lobe level bandwidth. So it is generally called side lobe separation. Bandwidth is the fifth one, and gain bandwidth sixth one. But generally, impedance bandwidth is considered. Okay, so these are the various bandwidth parameter for antenna. Concept of bandwidth is same, that is the range of frequency, but you are considering it for the range of frequency. Now here, the concept we are seeing, bandwidth is higher frequency. This is what called the percentage bandwidth. Higher frequency, lower frequency. The ratio of higher to lower frequency, it is called as percentage bandwidth. This is bandwidth high to low, one way. This is the percentage bandwidth. High frequency minus low frequency upon center frequency into 100. This is percentage bandwidth. Why this is given as why percentage bandwidth is considered? Because if you want to compare two antenna, the bandwidth is a simple concept. Okay, so for this is what graph you can see where this is what 10 dB. You can see bandwidth. You can see this line. This is what 10 dB. So sorry, this one is 10 dB. So this line is projected this way. So these 2 points are taken. So this is what the lower bandwidth, and this is what the higher bandwidth. So accordingly, you can nominate here. And this is what generally taken 9.5 dB standard, but practically it takes 10 dB. For practical purpose, minus 10 dB. This is what reflection coefficient. This is what reflection. This is I am talking about the impedance bandwidth. This is the example of impedance bandwidth. This is what the reflection coefficient, S11 parameter. Now reflection coefficient below 10 dB, and theoretically our standard is minus 9.5. You can say mention 9.5. So below 9.5, whatever the bandwidth you got, this band is operating this way. So below this is what your bandwidth. This is the range of frequency. This is bandwidth. This example is for impedance bandwidth. Now I will come for the percentage bandwidth. Now here percentage.
Sir, can you repeat again this
Okay.
that below diagram?
Okay. This is what the simple bandwidth concept of bandwidth. But here you must know that what should be the reference. Here you can say the reflection coefficient is mentioned here. This is what the reflection coefficient. Now, what is the reflection coefficient? It is S11 parameter. S parameters are there. How much, if you are transmitting to an antenna, how much will be reflection? Your waves are transmitted to the antenna and it is receiving some and reflecting some. So how much is the reflection? So that is what the most important parameter to understand. Now, what in most of the antenna parameters, some general antenna parameter maybe minus 6 dB is taken, but general standard is 9.5 dB. So what reference we are taken? Minus 9.5 dB as a reference, but practically it is taken as 10 dB. Okay, when I design the antenna and simulate it and practically, so 10 dB is general practical standard. Theoretically, it is mentioned 9.5 dB. So it is what equal to the 10% of the power is reflected back. It is what the indication of 10 dB. 10% is allowed. Okay, 90% तो जा रहा है या transmit हो रहा है या receive हो रहा है. So that way it is interpreted. Now Reflection coefficient is on the y-axis, आपका frequency range is on the x-axis. So this is what ये जो black is what the behavior of this particular antenna for this range of frequency. So for this range of frequency, it has here you can say here 5 dB reflection coefficient minus 5 dB. Then it is decreasing below 10 dB. So below 10 dB, this is what the range. ये जो range है bandwidth, this is below 10 dB. So whatever this range, suppose this is what maybe you can have, you can see here, whatever the frequency is here, that, and this is lower frequency, and this is higher frequency. So higher frequency minus lower frequency, as you calculate the bandwidth, that is what the bandwidth. Only the reference is this minus 9.5 dB. Is it clear? Or further any confusion?
Yes, sir, it is clear. But what is the practical application? I had seen many times, even like internship also, but got confused. Always we use this reference.
Practical
What is the
application.
reason behind?
Yeah, I'll explain. Practical application is better. You have designed antenna. Any antenna you have designed. You have designed for what purpose? Maybe transmitting or receiving.
Okay, yes.
Okay. But suppose we take an example of your RFID. Now, RFID is having frequency, I think in India, we are using 867.
868, right.
867, 868 is the band. Okay. So your antenna should receive and transmit. If it is receiving antenna, so it should receive that 867 and it should transmit that 867. It is a 2 megahertz band. Okay. 866 to 868. 867 is the center frequency. Okay. Now, how we will ensure that it is operating at that frequency? वो जो antenna है, it is receiving. How we will ensure? What is the mechanism you have? This is one of the mechanism. Here, by seeing this graph, ये graph आप अगर देखोगे, if this is 868 है, the higher frequency is 868, lower frequency is 866. ठीक है? Then 2 megahertz bandwidth you are getting, 867 is the center आपको मिल रहा है. So you are assured that this antenna, whatever you have designed, you can use it for RFID application. If it is not giving this frequency, then it will not work. Not work means suppose this band is shifted. Instead of this, ये आपका band जो है shift हो गया. ऐसा shift हो गया. Suppose ऐसा example देंगे. Now this is what your center frequency यहाँ आपको चाहिए 8. Suppose this is 867. तो आपका यहाँ shift होगा 8 something 900 की तरफ higher में. Is it applicable? नहीं, यहाँ पे 860
No, sir.
ये इतना ही दे रहा है ये. This much is giving. So this antenna you have to do changes in the design. You have to get it here. यहाँ पे ही लाना है for using it for RFID. Understood? This is what the practical application.
Okay, sir. Whatever application we are designing, we have to come into that range that is available for communication.
Yes. This is
For
what
that purposes we use this. Okay, understood.
This is what called the impedance bandwidth. Okay. Now we will come to the another parameter, same bandwidth. So यहाँ पे मैंने I have put here the percentage bandwidth. Now the upper frequency minus lower frequency जो है that bandwidth you calculate, that is okay. But why we require percentage bandwidth? Now percentage bandwidth. So why we require? Suppose I will take an application. An example लेता हूँ. What example? My higher frequency FH equals to 1 kilohertz. नहीं 1 नहीं. FH equals to suppose 5 kilohertz. And मेरा FL lower frequency equals to 3 kilohertz. ठीक है. तो मेरा बैंडविड्थ कितना हो गया? सिंपल बैंडविड्थ. Anybody? नॉर्मल बैंडविड्थ कितना हो गया?
2 kilohertz.
2 kilohertz. How you have calculated?
FH minus FL.
Okay, so this is simple, 2 kilohertz. But I'm giving the same example. It's a different example. Now my another FH is again equals to 5 megahertz. And FL equals to 3 megahertz. ओके, ठीक है, मेरा बैंडविड्थ कितना हो गया? What will be my bandwidth? Anyone?
2 megahertz.
2 megahertz. Simple, nothing great. Okay. So my bandwidth is 2 megahertz. Now the application one has a bandwidth of 2 kilohertz and the lower one is having bandwidth of 2 megahertz. तो किसका ज्यादा बैंडविड्थ है? Obviously 2 megahertz is higher, है ना? If I will see, आपको बोलूंगा 2 kilohertz is higher or 2 megahertz is higher. So what you will say? Which one is higher?
2 megahertz.
Obviously. But if I will take a percentage bandwidth, because these two different antenna are operating at different frequency. So I want to compare it. So if I will put in this formula, percentage bandwidth. Now what is percentage bandwidth? Higher frequency minus lower frequency upon center frequency into 100. अभी ये दोनों का center frequency suppose your FC equals to कितना 4 है, हाँ 4 kilohertz ऊपर वाले का, 4 megahertz नीचे वाले. So what will be the percentage bandwidth?
50%.
50%. दोनों का सेम रहेगा, डिफरेंट रहेगा? Is both have the same bandwidth or different bandwidth? Here also you will have 2 by 4 into 100. So first application which is having a bandwidth of 2 kilohertz, it will also give a bandwidth of how much? 50%. This also give a bandwidth of percentage bandwidth of 50%. So in this sense, percentage bandwidth of both the application is 50%. So both the antenna with reference to the percentage bandwidth are same. One is acting as megahertz, one is operating at lower frequency. So both the antennas having the 50% band. So if I want to compare antenna 1 and antenna 2, so both the antenna percentage bandwidth is same. So this is what if we want to compare antenna in reference to the bandwidth for differently operating frequencies, then this parameter is taken, that is what the percentage bandwidth. And this percentage bandwidth give us the comparison between these two antennas. So if I will take some another, that is the higher frequency is 5 and lower frequency is 1, and then I'll compare, then obviously the percentage bandwidth of the another antenna will change. But in this case, although they are operating at lower and higher frequency, but percentage bandwidth is same. So if I will claim, this is what, how I should claim that whether I have made the improved antenna or not. So we compare the percentage bandwidth. Okay, so that's why this is given here. Any doubt here?
Sir,
Yes.
what will be the unit of FC?
किसका percentage bandwidth का?
No, sir. That FC, like in kilohertz, megahertz, how we will come to know?
अब पहले एप्लीकेशन के लिए इट इज इन किलोहर्ट्ज, दूसरे एप्लीकेशन के लिए मेगाहर्ट्ज.
Acha, okay, depend upon condition, situation like which
Hmm.
in which unit we are dealing, right?
Hmm. इट इज द
Okay, sir.
डिफरेंस है ना, दोनों का डिफरेंस। मैंने दोनों एप्लीकेशन के लिए लिखा, इसके लिए यूनिट नहीं लिखा। इट इज फॉर फर्स्ट इट इज इन किलोहर्ट्ज, फॉर सेकंड इट इज इन मेगाहर्ट्ज। यहाँ पे लिखोगे, सपोज आई राइट हियर एफ सी, इसके लिए एफ सी लिखा, तो एफ सी इक्वल्स टू, सॉरी, 2 किलोहर्ट्ज। हाँ, this is 2 kilohertz for this example. For this example, fc equals to 4 megahertz. Correct? Correct?
Okay, sir.
So it is different. So the unit will be there, appropriate unit, kilohertz and megahertz. That will be there. Anything else?
No, sir.
Okay. So thank you. So this is what our concept for the bandwidth. So this is what the simple concept, but if you will understand this way, then you will get more interest in understanding. Okay. So FC, so one parameter VSWR. So appropriate VSWR for this you can note it down. Appropriate VSWR, voltage standing wave ratio. So appropriate VSWR for 9.5 dB के लिए है 2, less than 2. Okay. So sometimes we take VSWR, voltage standing wave ratio. Here जो y-axis है reflection coefficient, or you can take voltage standing wave ratio. So if you are taking voltage standing wave ratio, then it should be 2. It is unitless. If you are taking reflection coefficient, then it is minus 9.5 dB. Okay, so this you please note it down. So these are the requirement. Again, both within the impedance bandwidth. Okay. Now this is what the small. We will take this and then we'll stop. Antenna radiation fields. So this is simple concept. So here now further you will require the radiation fields. Now when antenna radiate, the fields of the antenna are bifurcate into 3 types. Now what are those 3 types? One is the, this is this is the reactive near field. Then radiating near field, and last one is the far field. So we are not much doing calculation in these two. We are doing much calculation in the far field. Far field, when the far field we are considering, the far field is what actually antenna radiation means, antenna acting as a transmitter and receiver. It is in far field. This is a reactive near field. The near field means दो bifurcation. This is both are near field. So one is a reactive near, another is a radiating near. Now this is what your antenna. So from this to this distance, ये जो भी distance here, this is what a reactive field, and this is what radiative. So beyond this, this is the radiative field, and this is what far field. Okay, इसके आगे far field. Far field is there. Now, how we will understand which one is the reactive near field? R is the distance. 0.62 under root of D3 by lambda. What is D? So here D is the maximum dimension of an antenna. So if you will take, this is the dipole antenna. If it has a dimension of whatever 10 centimeter, so that 10 centimeter, and you are operating at what frequency, you take the appropriate lambda. So this 10 cube means 10 square will be 100 and 10 cube will be 1000. Am I right? So 1000 by lambda, and you will can calculate this distance. So this will be, you will get in centimeter, as dr and lambda, all this you are taking in centimeter. If you are taking, so you will get the reactive near field. Okay. So below this, from 0 to this much distance is reactive near field. Radiating near field is 2d square by lambda. So it is 2d. D is the maximum dimension. For this antenna, the maximum dimension is 10 centimeter. Okay. So 10 centimeter is the maximum dimension for this antenna. So 10 square, 100, 200. So 200 by lambda. This is one example I am taking. This is R2. So till this, suppose your 200 and your lambda is 5, maybe 10, suppose 10. So 200 by 10, so it is 20. So till 20 centimeter, you will have this radiative near field. And far field is beyond this. What? 2d square by lambda. Beyond this, beyond what we have calculated, 20 centimeter. Beyond 20 centimeter, it is far field. So in both the diagram, it is shown. This is R1, this is R2, and this is far field. So this is what simple concept, but it is required that to understand. Minimum distance between transmitting and receiving antenna must be greater than this much. How much? This 2d square by lambda. इससे ज़्यादा होना चाहिए. Then and then the antenna can be used as a transmitter and receiver. This is what the thing here. So in some calculations, we are using this mainly the radiation pattern calculation. This the distance between the transmitting, if you want to experimentally, if you want to calculate the radiation pattern of an antenna, then the minimum distance between transmitting and receiving antenna must be greater than this. That is 2d square by lambda. So these are the notations for this. This is antenna radiation. This is a simple concept, nothing great here. And it is common to all type, any type of antenna. So here this D is shown maximum dimension. So whatever D, whatever the maximum dimension of antenna, whether it is a wire antenna, whether it's a planar antenna, whether it is a non-planar antenna, any antenna. So you can take a maximum dimension of that antenna is D. This way we can consider the radiation fields. Is there any doubt here? Radiation fields? I don't think so. So it is very simple concept. So here we will stop for a day.